All right, now we're ready to, now that we've identified the types of intermolecular forces, we're ready to look at the application of those to the properties of liquids. So in the picture here we see kind of a beaker of typical liquids, and obviously you have the interactions between like particles. So if this were a particular solvent or a liquid, the particles that are the same. But then you also have the interactions between unlike particles, for instance the dipole ion attractions that you get with water and ionic substances. We'll also see that the liquid has interactions with the container as well. So those are going to be things we might look at. So the three pictures here describe three of the things we normally look at or phenomena with water. Over on the left, we have two different weights of motor oil. And so this is looking at what's called the viscosity. So what it's demonstrating is that the oil on the right is less viscous, so it's able to flow out of the tube faster and fill up the cylinder. And the one on the left is more viscous or thick, we think of it. So syrup is very viscous. And the attractive forces then, the more viscous it is, let's get an indication that the attractive forces in the liquid are stronger. Or conversely, if you have strong intermolecular forces, they would have a high viscosity. So down at the bottom you can see some formulas for different hydrocarbons, and noting the viscosity. As the number of hydrocarbons gets larger, we have larger London dispersion forces, and consequently we get a higher viscosity for those liquids. In the middle, we have surface tension. Right? And this is what allows things to float on the surface of water. You may have in middle school floated a paper clip or a needle on top of water. Even though that paper clip and the needle are more dense than water, the attractive forces between the water molecules, those hydrogen bonds are very strong, and so they can actually support the weight or the force of things that actually would be more dense than the water. And then over on the right, we have what's called the capillary rise action. And in the test tube on the left, you see water where you have a meniscus here. And that's due to the water molecules having adhesive forces of attraction for the glass. And so in this case, the adhesion versus cohesion. So the adhesion is the force of attraction between water and the glass, and the cohesion, the cohesive forces, are the forces between the water molecules themselves. And so you can see that there's a stronger attraction between the water and the glass than the water and the water. And so you get the water actually climbing up the side and creating that meniscus. On the right, you see mercury. Mercury has relatively strong attractive forces and very weak cohesive or very weak adhesive forces for the glass. So the mercury actually forms a meniscus that's in the opposite direction because the mercury molecules or mercury atoms actually have stronger cohesive forces than adhesive forces for the glass. Here we have a chart describing the changes of state, or the phase changes. So again, this shouldn't be anything horribly new to us. We can, any change that goes up, so for instance from solid to liquid or liquid to gas, any of those things are going to require an addition of energy to overcome the attractive forces. And in order to take things down, we would remove energy so that the attractive forces could then pull those molecules closer together. So going gas to liquid and liquid to solid. And then, of course, the kind of less common situation of sublimation going from solid directly to gas, or deposition going from gas directly to solid. In terms of the energy changes that are required for these things, we have the heat of fusion, which is the energy required to melt something, change from solid to liquid, and the heat of vaporization, which is the energy required to vaporize something. So here we have both of those values for three different substances: butane, diethyl ether, water, and mercury. So the first thing we want to notice is that obviously the attractive forces in these things are going to play an important role in the amount of energy required to to either melt something or vaporize something. We already talked about in class of how the way the substance is packed together plays a role in that as well. But for all of these things, you can see that there's a significant difference, or the heat of vaporization of the gas, heat of vaporization going from gas to liquid to gas, is much higher than the heat of fusion going from solid to liquid. And the reason for that is because when you go from a solid to a liquid, the molecules just have to overcome the attractive forces enough so that they can move around amongst themselves. Whereas when you go from a liquid to a gas, those particles actually have to move quite a ways apart. And so you've got to put a lot more energy in to do that. And then we'll look at this. So it's from a kind of a qualitative sense. We'll look at a quantitative sense in just a minute. Here's a heating curve for water. It might be a good exercise for you to sketch a cooling curve for water. We might want to note here that on the bottom axis here, the x-axis, we're thinking about adding heat, which usually happens as time goes on. We want to remember that as we're adding heat to the water, we can think of water's energy as having two components. This would be the internal energy. There would be a potential energy component to the water, as well as a kinetic energy component. So as we're adding energy to this, we can add it to either one of these, quote, energy accounts. We can either increase the potential energy of the water molecules, or we can increase their kinetic energy. Kinetic energy, since it's a function, or it's measured by the temperature, when we look at the curve, any area of the curve where there's a change in temperature would indicate that there's a change in kinetic energy. So for instance, from A to B, here would be a change in kinetic energy because there's a temperature change. From C to D would be a change in the kinetic energy, and from E to F would represent a change in the kinetic energy. If you look at the horizontal lines from B to C or D to E, we're still adding energy there. So that energy must be going into the potential energy of the water molecules. And the change of potential energy is based on position. So that B to C part is where we're taking that solid, the ice, and we're changing it to liquid. And the D to E part, we're taking the liquid water and we're changing the position of the molecules so that they will change into a vapor. So again, being able to analyze this graph from a standpoint of kinetic and potential energy of the water molecules is an important idea for us to have. The other thing we want to do from this graph is be able to answer quantitatively different types of problems. So for instance, the one that's given here, determine the amount of energy required to change 10 grams of water at -5 degrees Celsius to gas at 10 degrees, or at 100 degrees Celsius. What I'm going to do first is trace out this change on my graph. So I'm starting at -5 degrees Celsius, which is about right there. So the first thing I'm going to have to do to get up to here, point E is my final point, the gas at 100 degrees. First thing I'm going to have to do is heat that solid up to point B so that it will be at 0 degrees. Right, so I'm still in the solid state. The next step, so I'm going to call that Q2, Q1. Right, so the heat added to go from -5 degrees to B. Then I'm going to have to go from B to C, right, so that's changing the potential energy. I'm going to call that Q2. Then I have to go from C all the way up to D, right, so there's a change in kinetic energy. I'm going to call that Q3. And then I'll go from D to my ending point, E. Again, a change in potential energy, so I'm going to call that Q4. Right, so calculating these, we're going to have 4 different calculations that we'll do. So here are the 4 different calculations that we're going to have. So for Q1, we have a mass of water, change in temperature, and specific heat. And the specific heat has to be for the state of matter that you're in, which is a solid. So you can see I plugged the numbers in here, 10 grams times T final minus T initial times the specific heat of the solid. Q2, we undergo a change of state. So we're going to use the heat of fusion, so mass, 10 grams times 333 joules per gram. This is specific for water, as is the specific heat. Q3, we're changing temperature again, so we're going back to original temperature. Mass, delta T, specific heat, only this time we've got the specific heat of the liquid. Q4, mass times, again, we're going through a change of state now, so it's the heat of vaporization. So if I plug those values in, and then I would get my total energy it would take to do this by adding all of those up together. Now, each question is going to be slightly different, so you'll want to kind of diagram the change and then figure out which of these equations you would need to do for a particular problem. Now, the specifics of these states of matter we'll get into in the next section, which will focus in on what are called phase diagrams.